Hey, welcome back. Starting your exciting journey into calculus. Calculus was discovered by Newton and Leibniz around the same time, and we're going to start the journey right now. And I've got here a few little screen clippings from Hayes and Harris of graphs and stuff that are going to relate to the fundamental theorem of calculus, and we'll be doing quite a bit of this during this course. This is just going to give you an introduction to it right at the end there of chapter 2 in Hayes and Harris. Let's go down, and here it is, 2D. The basic theory of calculus, the fundamental theorem of calculus, has to do with rates of change. If, for example, you're measuring how rapidly one quantity is changing with respect to the other, how could you find the actual value of the quantity going backwards from its rate of change? And the best example of that, of course, is if you know the speed of a car, which is a change in distance with time. How do you connect that with the actual distance travelled? So it's a rate of change of something relating to the actual value of that quantity. That's what calculus is about. If you were to roughly say we're in calculus, we're looking at rates of change, I suppose that wouldn't be a bad initial description. And then, of course, going the other way, if you have a quantity, how can you find its rate of change? So if you have the distance a car is travelling, how do you find its speed? Because the speed is the rate of change of distance. So it's all that sort of thing. You might say, well, gee, that sounds very simple to me. And it really is. Let's have a look at some, I suppose, more difficult situations we can get into with this distance idea and speeds of cars. So let's go down now and have a look at a problem. So here we are. We know that a car is travelling at a constant speed of 80 kilometres an hour. And at the moment it's 200 kilometres from Adelaide. Draw the graph of the speed of the car against time. So at 0 time here, the car is travelling at 80 kilometres an hour. It's constant, so it's 200 kilometres from Adelaide, which doesn't have any bearing on this particular graph, because there's 200 kilometres from Adelaide, but this is not a distance graph, and so it maintains that 80 kilometres per hour for all time. And what about trying to calculate the distance here that it travels in any particular time? What would you actually do? Let's have a look then at doing this. The distance travelled in t hours, and so you might say, well, speed was distance travelled, or the change in displacement with time. Just bringing in this symbol, this triangle, which is a Greek capital delta, and we use that in mathematics to imply change in. So in studying calculus, we quite often would use that delta symbol. So speed is change in distance with time, or displacement s with time. So here the speed times the time should give the number of kilometres. So we're basically multiplying this out here. And multiply by the time, you should get the change in displacement. The interesting thing in the graph is this, and that is that the ATT is actually the area of this section here. So if you put t hours and you're multiplying by the speed to get the distance, that's 80 times t, that is actually that shaded area there. That's interesting. The actual value of the quantity whose rate of change is given, that is the distance, a change in the distance with time is the speed. The actual value of the distance is the area under the rate of change graph. Because this is a rate of change, isn't it? This is a change in displacement with time. And so to get S from this, what do we do? S is the area under the rate of change graph. Okay. That is between that graph and the x-axis, or the t-axis there. Okay, so let's keep going then. That's an interesting point. Then the question says, well, can you have a look at the distance, the quantity? Because we looked at a graph of the change in the quantity, the change in distance with time, which is the speed. Now let's put distance up here using s, displacement in actual fact, usually we say that. So here, this is time. So we're drawing a graph now of how far the body is travelling. So it starts off 200 kilometres from Adelaide, so at t equals 0, it's that. And every 1 hour, of course, it's a straight line. Why is it a straight line? Well, of course, it's a constant speed. So what that means is every time we move 1 hour's worth, it's going to go up 80 kilometres. So here in the next hour, this step up is going to be the same. And in the next hour, the step up is going to be the same. So every time we go 1 hour's worth, we go another 80 kilometres. All right, so that's the idea. What we need to do now is to say, well, okay, can you see that there's an important relationship I've just mentioned there, that the change in displacement with time, which is the slope of the line, isn't it? The slope is a change in the dependent variable divided by the change in the independent variable, or the old y step on x step. Here it's the distance step on the t step, putting it in the context. Remember, just keep in mind we have y step on x step for the slope usually, and that's what they're working out here. But in this context, it's the s step on the t step, if you like, in the context of this question. Okay, so the slope of the line is the speed of the car. We can see that. So that's just a bit of a revision now on relationship between a very important rate of change quantity, the speed, with respect to distance, the thing that it's measuring the rate of change of. Okay, so we've got that. Well, let's practice some of that basic stuff now, and let's do some problems here. So here's exactly the same sort of problem. I want you to try and repeat the steps here that were done up in the example, and do the same sort of thing. Just notice here an interpretation of the slope and the s-intercept of this line. Just remember now, this is a contextual subject, a utility subject, a practical application. So this interpretation should be a practical, contextual explanation, not just mathematics, not just a rate of change thing. Practical, contextual interpretation. And this is very important in this course, that you're able to see what the fundamental mathematical concepts really mean in the context or the practical aspect of the problem. Okay, so now they're going to, in this problem, ask you to look at a different rate of change. Speed is the rate of change of distance with time, displacement with time. Here we're talking about the rate of change of the people entering in a sports stadium. So how is that changing with time? The number of people entering the sports stadium. And we have a rate of change here. So this is like a speed type problem. It's not the rate of change of displacement or distance with time. It's the rate of change of the people with time. So, food for thought there. We'll just go down and have a look at these couple here. Same thing. Question 3. here we are. Can you see now rate of change problems are characterised by something per time, litres per time. The quantity is changing per time. So that gives you an idea that you're talking about in all of these problems, I think. I'll just do a little bit better there than that, I think. Of all these problems, what we're doing, not going well there, is if that's time, this is something changing with time. So this might be volume per time, delta V on delta T, up there. Or people entering the stadium, delta P on delta T. But we're always looking in these problems. This is what characterises calculus, at a rate of change of something. Okay, so let's have a look at question 4. Drugs are generally cleared from the body, so, here's a rate of change. How fast alcohol is cleared from the body. Alcohol's a poison, and the body tries to clear it. Okay, it's identified by the liver as a poison, and it actually slows the body down and poisons it. So the body tries to get rid of it, and here's the rate of clearance, and it's generally going to be at a constant rate. So we can see then that you could draw the same sort of graph. So I want you to have a go at these, and we'll have a look at the solutions in a minute. There's a theoretical one here where you're drawing the function f of x equals c. So the function takes a constant value. So it's going to look again like what we had before. But I want you to do it in theory land now. So this is a purely mathematical or theoretical approach to what we've been doing. So use those 4 examples up above to get a bit of a handle on this constant rate of change. And then can you generalise it for people coming along and saying, well, we can see the function we're drawing is changing, but if we made it a general function f of x equals c, what would the rest of the problem look like? Okay, and they do it down here. Question 5 covers all the previous questions because it's a generalisation, isn't it? It's a generalisation. Instead of a particular function meaning something, we're talking about it having a constant value. We're talking about it just being f of x. Okay, well let's go down now and have a look at the solutions. I'll come to there, so you'll be able to go back, do the problems, toggle back, then come forward and toggle around and get the answers. So we'll just put it down there. We get a window with eventually covering all of them. You can check them off there and pause the presentation. So there are the other two over on that side. Okay, so I would suggest now you toggle back to the problems, pause it, have a go at question 1, toggle forward, mark it, and so on, and just check yourself out there. Okay, so you can do that. Now I'm going to move on now, so let's go to an interesting question, because I don't think you've actually learnt much yet. But here's a problem. Houston, we have a problem here, I think. Because of what? Well, if we consider this to be a speed, we've only got y and x, so doing it in general land now. But can you see that this quantity is not changing uniformly? This is a curve. So if it was the speed again up here, that was speed. The body is speeding up, isn't it? Keeps speeding up faster and faster. Ooh. Okay, well the distance is going to be the area under the curve, but hang on. Does anybody know a formula for the area of a shape like that? I don't think so. This is not a known geometric shape, if you like. No formula. back before, do you remember, we had this. Say, that's a rectangle, mate. That's length by breadth. Easy peasy. That one. That's for a straight line. This is a constant value here for y. And this time it isn't. It's not a known geometric shape. So we're in trouble. Because we don't know how to find that area exactly, because the curviness is dictated by that function, x squared plus 1. And between 1 and 4, that isn't a regular geometric shape. All right, well, what could we do? Well, we could try and estimate it. Not very good maths, eh? But we could try to estimate that area. How would we do it? Let's look at a process that leads to the fundamental theorem of calculus here and see. Okay, well, let's have a look at estimating the area. So over here, let's divide the x interval up into equal parts. See, it's one unit, and 1 unit. So we're going to make rectangles here. We're going to make rectangles that go from the first scale unit to the second, and we're going to draw what we call an upper rectangle. So you start within any interval, you start at the highest point and go backwards. Or if it was downwards, if the function was decreasing, you'd be going the other way. So in the next interval, over this interval here now, you take the highest point and go backwards. So you've got upper rectangles. Why do that? Well, that gives us some idea of the area which is above that which we want. Remember, what we want is actually only shaded under there. And if we did it over here, come over here, if we did a lower rectangle sum, so we go to the starting point of the interval and the end point, and we take the lowest value and draw across. So in the next interval, that's the lowest value, and we draw across. So this creates rectangles that lie under the curve. So somehow, this area that we want, up under there, is somewhere between the upper sum of rectangles and the lower, somewhere in between. So we could say if the area is A, it's less than the upper area, but it's greater than the lower area. So sandwiched somewhere in between. Now, and the book here, A.J. Naris, actually writes it in that way. Can we work out these upper and lower sums? Well, let's come over to the lower one. How would you work out this rectangle in here? Well, it's 1 unit wide, there it is there, and the height of it is given by that value there, isn't it? That's f of 1. If you substituted 1 in here, 1 squared plus 1 is 2, so it would be 1 by 2. There it is. And then we go to the next point. That little rectangle in there, I'll just rub this out now so that you can actually see it better. This is 1 unit long, the length. What's its height? There's its height there. So how tall is that? Well, that's the value here that you get when you sub 2 into the function. The height of that is 5, so it's 1 times 5 is 5. Now, it's very, very important when you're working these areas out that you don't read across. See, I was nearly going to do that there. You don't read across, because you can't be sure that this lines up perfectly. In this case it does, but in general that's a big no-no. You must find the height of these rectangles using proper mathematics. This is another interval of 1, so it's a width of 1 times what's the height here? Well, it's whatever 3 gives you when you sub it in the function. That's that height, the function value at 3. Those 3 3s are 9 plus 1 is 10. So you can actually find the sum of those under rectangles, the lower rectangle sum. You can do the same thing over here. Can we just get rid of this again here so we see what we're doing? What's the area of this rectangle? It's above now, so it's again 1 unit long. And how tall? When you put 2 in this function, you get a height of 5, because 2 squared plus 1 is 5. So f of 2 is 5. And that's the way we should always find the heights of these. Let's go across to the next one, which is this little dude here. How tall is it? That height is given by putting 3 in the function. So it comes to 10. So we've got 5 and then 10. And then the last one, this height here, is obtained by putting 4 into the function. You get 17. So they are all calculations of the areas of the rectangles. So on this one now we have 32. On this one we have 17. So our area is jammed somewhere between less than 32 but greater than 17. I guess you're going to say to me, Huddy, what are you doing? This doesn't seem to be very good maths. We've only got an estimate for the area. Can't we do better? All right, you're going to make me do it. Here we are. Let's do better. Okay, so if we try to do better than this, here we are. This is what the area is, somewhere between 17 and 32 square units. Not good enough. Oh, here's an idea. We could divide it up into smaller rectangles. Okay, so from 1 to 4, instead of having 3 rectangles, we could have 6. So in other words, start to make more rectangles. So what would that mean? Well, there'd be 1 there, and then, oops, where are we? 1 here, and then 1 there, and where are we here? 1 there. I think we're getting it right here. Then in the next interval, 1 there, and 1 there, I think. Okay, so we're going to do more rectangles above that line over here, same thing. Split it up into half units. And so from there to there, that's 1. There's see what's going to happen. They're all going to be underneath then. Okay, now we can do some under rectangles or lower sums. So what's the calculation? This time it's a half. If we make that smaller, half a unit long, and then we want to multiply by the height of that one, 1, and then here the height of this one here is f of 1.5, and then f of 2, this next one. You can see what's happening. There's going to be 6 of them now because we're making more rectangles. And we're going to get an answer here, doing some decimal places, 20.375 square units. Please remember, do not read off the height of the rectangle from the vertical axis there. It's too inaccurate. You must sub into here. So if I want to do f of 2.5, that is the accurate way of doing it. 2.5 squared plus 1. Do not read off that vertical scale. Too inaccurate. Okay, and over here we've got the same thing, haven't we? So it's a half by, what's the height here? The highest one, that's going to be f of 1.5. Well, we're making rectangles which are only half as wide now. Do you see, can you see this? What's happening? We're getting different totals for our upper and lower sums. More accurate, aren't they? Coming closer to that curve from above and from underneath. So they must be getting closer to the actual value of the area. So here it is, we've got this again. So what's it jammed between now? It's jammed between 27.875 and 20.375 square units. Ooh, this is interesting. This is more accurate. This is more accurate. It's sort of sometimes referred to as a sandwich theorem, where one end of an inequality, this is an inequality, isn't it? Something is less than something else but greater than the other one. So these are inequality signs. So it's sometimes called a sandwich theorem, where the quantity you're trying to find is sandwiched between two values that are approaching each other. Are they going to approach each other? What do you think? How could you possibly improve the estimate again? Okay, let's have a look at a problem. Hayes Harris got one down here now. Car travels at the speed of this. Oh, that's a different looking function. Never seen one like that. Well, you haven't anyway. Before, but remember, you've got technology, so you don't have to be frightened by this function. It is a type of rational function, isn't it? Because we've got a function in the bottom line there, a ratio. The time t after it leaves the city is given in that formula there. Sketch a graph. So use technology to the rescue here. Just remembering your graph must have a good scale here. And I don't like y. No, it's not y, it's v, so that's all right, v for velocity. And this has to be labelled. We should actually have units there as well. What are kilometres and hours, and we must have key points and shape. Just keep that in mind, it's going to be important later in this course. There are 3 marks involved here, and they're easy marks to get if you're careful. Must have label of the axes, key points and shape. Okay, you can see the function is increasing. How do you know that? Because what you say, if you're looking at an increasing or decreasing function, you always move along the independent variable axis. As this increases, you ask the question, what happens to the vertical axis values? That's what you ask. So here, this is as this increases, we see that is increasing. So therefore it's an increasing function. You look at what's happening up the vertical axis as you move positively or increasing along the horizontal axis. So it is an increasing function, and we can divide it up into 4 sections if you like, and see what's going to happen here. It's going to increase from 50 kilometres an hour, and how far will the body go? Well, it's going to go more than 1 hour's worth of 50, isn't it? Okay, so here the distance represented from that to that is going to be more than 1 by 50. 1 by 50 is only that. It's going to go more than 50 kilometres, which is just that distance in there, because it is an increasing function, and you've got this extra up here. Okay, so what could we do to do a better estimate, or to get an estimate in the first 4 hours of travelling here? If we wanted to do that, we would have these areas here. There's an upper, I put the upper and lower, some left and right there. So you can see the upper one. Remember, how do you draw it? You go to the start of the interval, go to the end of the interval, you take the highest value and go back or forward to the other one. So here, go into this interval, go to the highest point in the interval, join it back. So that's an idea of how to draw those rectangles. So here we're trying to estimate, remember the question here, we want to sketch a graph and estimate this graph of estimate the distance in after 4 hours. So here we're going to do the lower sum as well. Go to the interval, there and there, take the lowest point on that interval and draw across to the end of the interval. So it's the same basic method, so let's try and put the steps down. Number 1, mark interval, here they are 1 unit interval, mark interval endpoints. Upper rectangles, take highest value in the interval. Lower rectangles, take the lowest value across that interval, and then join back to other end of interval to make a rectangle. Okay. So you can do it for a decreasing function as well, because with a decreasing function we've got this. So with a decreasing function, if you were to take an intervals like that, how does it work? Right, you start at the ends of the interval. If you're doing an upper sum, which one's higher? That one's higher, and you go along to the next one. There's on the next interval here, let's make a lower rectangle. So there's the start and there's the end of the interval. So how would you make a lower rectangle? Go to the lowest point in the interval and join back to the end of the interval. So you can make up or low. You wouldn't do an upper and lower in the one problem. I'm just giving you an example of how to think about it. So you mark the interval endpoints. Upper rectangles take the highest value across that interval, picking the highest value one of the endpoints. Lower ones take the lowest value and then join back to the other end of the interval to produce a rectangle. So do you agree with these? 1 unit long, multiplying by the heights by careful substitution. You can't read it off, you must see these values. They are quite a bit more difficult to work with here, and so is the function. So you've actually got to substitute, let's say here, this one v of 2. So what do? You go back and put it in this function here to get v of 2. So you need to do that to get the accuracy there. Alright, so we have an upper and lower sum, and therefore the total distance is somewhere between 338.2 kilometres and 387.6. So looking at that. Now, we could do what we did before, and that's divided up into smaller parts, more rectangles. So 2 ways of thinking of increasing the accuracy. A smaller rectangle widths, which implies more rectangles. That's going to give you a greater accuracy. Okay, so a couple of ways of saying that. You can either say, well, I'm going to make the rectangles smaller in width, or I'm just going to have more of them. Either way. Can you see, and this is starting to get interesting here, can you see that the difference between these is actually getting less, because the rectangles with that smaller width are coming closer to the same area, and therefore here's our inequality again now. The actual area, or the total distance in this context, is jammed between 354.8 and 379.5. All right, very good. Time for you to have a go. Okay, so here, first 2 questions. Sketch a graph, unfamiliar function. It is a rate of change. some quantity per time as its changing value. So you're not phased by that function because you're going to use technology, right? And then you copy it onto your paper, remembering there are 3 marks, must have the scale and the units and the labels of those scales accurately, must have the key points and a good shape, so you need to trace that off of the calculator. Okay, and then you can start to draw quite accurately the rectangles. Okay, and here of course they are suggesting you keep in mind, if your estimate's a bit rough, you can draw more rectangles and have a smaller width between the across the interval. Okay, so I'll get you to try to do those problems. So just have a look there and pause the presentation later. We'll come up to questions 3 and 4. So as you move down, toggle backwards and forwards to the question and have some fun with that. Here are the solutions. So when you've had a go, I think I'll have to do that, doesn't fit on there. Mark 1 to D. We'll just go forward there a bit. And there's E and part of question 2 there. And if we keep going, 2D. Okay. And just on question 3. See if we can put it there. Question 3. And then question 4. Okay. So what I'd like you to do is to rewind, toggle back there, and have a go at those problems as you move it down. Then go forward and mark your work and see how you go. Do you know that I have avoided your question? You said it back at the beginning, I put the words in your mouth, Huddy, this is pretty rough mathematics because we're only doing an estimate. Uh-oh, I haven't answered that. All we've done is gotten a better estimate. Are you disappointed? Aren't you saying, hey, can't maths do better? Can't maths get an exact answer? I hope, budding young mathematician that you are, I hope that you are thinking that. What would be the exact area? Mathematics usually enables us to calculate exact values, or certainly not have such a rough estimate as this. And that's where the fundamental theorem of calculus is going to come to our rescue. So that excitement has got to wait till the next presentation, 4B. So I want you to do some good work on this. This is really important, this last little bit now, to this course. So I wish you good luck and enjoyment with that. But for now, it's cheers from me. I'll catch you in the next presentation.